Assalamu alaikum and very good evening to all of you. I hope you had a good day so far. In today's video, I'm going to explain Stone-Geary utility function and how to derive demand functions using a Stone-Geary utility function. Let me give you some background information about the Stone-Geary utility function. The Stone-Geary utility function was first derived by Roy Gary in 1950 in a comment on an earlier research work conducted by Lawrence Klein and Herman Rubin. Richard Stone was, on the other hand, the first to estimate the linear expenditure system. The Stone-Geary utility function is an extension of the Cobb-Douglas utility function that allows us to consider some subsistence level of consumption which need to be guaranteed before full consumption demand is determined. This is straightforward and I would like to explain this. The interesting property of the Stone-Geary utility function is that its demand function yields a linear expenditure system. As I mentioned earlier, Richard Stone used the function derived by Gary, and he tried to estimate the linear expenditure system. So that is why this utility function carries name of Stone-Geary, properly known as the Stone-Geary utility function. For any good, the total expenditure is the sum of a fixed level of expenditure allotted for the subsistence level of consumption and a fixed proportion of the leftover income once the minimum or the subsistence level of consumptions are accounted for. That indicates the variable part of consumption demand. For the n good case, the Stone-Geary utility function is defined by the following equation, where the utility function for good x1, x2 up to xn is equal to x1 minus z1 raised to the power alpha 1 times x2 minus z2 to the power alpha 2 up to xn minus zn raised to the power alpha n, and that is equal to the product of xj minus zj raised to the power alpha j, where j varies from 1 to n. So this is equation number 1, and this means that the Stone-Geary utility function is the product of xj minus zj raised to the power alpha j, where j varies from 1 to n. And here z is a non-negative number that is greater than or equal to 0, and these are the minimum levels of consumption, and alpha j non-negative weights that add up to 1. The utility maximization problem under the budget constraint imposed by the income level M and given minimum consumption Zj is given by this function. So the constraint maximization problem of the economic agent is to maximize utility from the consumption of good x1, x2 up to xn, and that is equal to the product of this difference between xj and zj raised to the power alpha j, where j varies from 1 to n, and the budget constraint is that the sum of the expenditure, that is summation j varies from 1 to n, price of j times consumption of xj is equal to m, and xj is greater than or equal to zj. So this is the budget constraint. The solution of this problem is straightforward. If we perform some change of the variable, let us define that the difference between xi and zi is equal to yi, and m prime is equal to m minus summation j varies from 1 to n pj times zj, and This is equation number 2. We then solve the reformulated and back to the standard Cobb-Douglas function to find that the Marshallian demand for yi is equal to alpha I times m prime divided by pi, and it means that the Marshallian demand curve for this reformulated variable yi is a positive function of the leftover income, and it is inversely related to the price of this reformulated variable. So this is just like a Marshallian demand curve, just like in Cobb-Douglas production function. Now, if we undo the change of variable, then we obtain that xj is equal to zj plus alpha j divided by pj times m minus summation I varies from 1 to n pi zi. So this is how we can derive demand function from Stone-Geary utility function. This solution yields a demand system which has the linear expenditure property. The expenditure on good J includes two parts, that is the fixed part, which is given by value at the current price of the minimal consumption of J, and a variable part, that is alpha j, proportional to the leftover level of income after the consumer incurs in the expenditure of the minimal consumption level. So it means that the total expenditure on good J has two parts. One is the fixed part and the other one is the variable part. The fixed part is given by the value at the current price of the subsistence level of consumption of J, and then there is a variable part, that is alpha j, proportional to the income which is left over after the consumer has consumed the minimal or the subsistence consumption levels. So we have pj xj, that is the consumption expenditure on xj, and that is equal to pj zj plus alpha j times m minus summation I varies from 1 to n pi zi. Notice that with no minimum consumption levels, if all zi are 0, the demand function in equation 3 reverts, of course, to the standard Cobb-Douglas demand function as I mentioned earlier, and in that case the demand function is a positive function or direct function of the level of income, but inverse function of the own price. But because of linearity that we observe in expression 4, we commonly refer to this Stone-Geary demand system as the linear expenditure system as well. So that is why, as I mentioned earlier, that Richard Stone was the first person to estimate the linear expenditure function using the utility function, which was first derived by Roy Gary. We must note that both these demand curves are downward sloping with respect to its own price. So this means that there is a little bit difference between Cobb-Douglas production function and the Stone-Geary utility function. They differ only in the sense that in case of Stone-Geary utility function, the consumer consumes some minimum level of goods, and then whatever income is left over after spending on the subsistence level of these goods, then that money is consumed on the purchase of these goods over and above the subsistence level. So this is one of the most interesting and challenging utility function, and the demand system is associated with Stone-Geary utility function is different than those derived in case of Cobb-Douglas production function. But if all Zj are equal to 0, then Stone-Geary utility function reverts back to standard Cobb-Douglas utility function. I hope you liked it. Kindly share this channel with your friends, with your colleagues, and with your students. Kindly subscribe to the channel and don't forget to click on the bell icon so that you can get regular notifications about my other videos that I'll upload for you.